This section covers extrema and the first derivative test. I just want to mention, as we come across this new material, please keep in mind, although we will be introducing some new terminology, some definitions, most of the math that we need to handle these ideas, the new and the old, actually come from what we learned in previous sections, especially that last section. Plus, I would say a large dose of common sense. If you just look at things from a common sense perspective, I think you're going to find this a lot easier. And this is especially true when we're working with polynomial functions, and that's because, as we know, polynomial functions are very well behaved. They're continuous and have no holes, no gaps, no jumps, just very well behaved functions. So when we're dealing with polynomials, this is going to be especially straightforward. Having said that, let's just jump in. And as one more aside, I do want to mention that probably 80 to 90% of the work that we're going to be doing solving these problems revolve around building these increasing, decreasing charts that we learned how to do in the previous section. So you really need to be good at that. And if you're not, you might want to go back and review that, because it's really the heart of what we do in this section. Practice this. Make sure you're good at it, because this little increasing, decreasing chart is the heart of what we'll be doing. And apart from learning these new definitions, some terminology, I'm determined to convince you that you basically already know what you need to know to do these problems. So don't get distracted by the details. Just remember, most of this material, you really already know how to do the math. Let's start off with an example. Suppose I give you the function f of x equal 1/3 x cubed minus x and ask you to find all the relative extrema of the function. I told you we'll be introducing some new terminology, so the first thing you might ask is, what does relative extrema mean? It's actually pretty simple. If you think about real-life problems, physics, engineering, business, often it's really important to find the maximum value or the minimum value of the function. What's the maximum profit that a business can expect to make from producing a certain number of items? What's the minimum energy required to get some job done? It's a very common thing to need to know how to do. And fortunately, what we've learned about critical values and intervals and building this increasing, decreasing chart from the previous section is actually the foundation for doing just that. For example, suppose I give you this function. We know that if it's increasing on the left of a point, and then it's at that point it turns down and starts decreasing, just looking at that graph, you can see that the graph had reached a maximum value at that point, and the x value of that point we're going to call a critical number. At that point where the graph was changing from increasing to decreasing, at what we'll call a critical number, is something we'll call a relative maximum. On the other hand, if the curve is going down and then all of a sudden turns up, it's going from decreasing to increasing, you've hit a critical number which represents a relative minimum of the function. So a relative maximum is sort of like a hill top, and a relative minimum is sort of like a valley bottom. These type of function values are called relative extrema. Extrema is a catch-all term for maximum and minimum all thrown together. So if you don't know if it's a max or min, or you don't want to distinguish, you can just call it a relative extrema. But it's either a relative max or a relative min. Now let's go back to our example that we left off to talk about this terminology. That function was f of x equals 1/3 x cubed minus x. As I've mentioned, you really want to construct an increasing, decreasing chart, which means the very first thing you want to do is take the derivative. This is a simple polynomial function whose derivative is 3 times 1/3, which is 1, x to the 1 less than 3 is x squared, minus, and the derivative of x is 1. So the derivative f prime of x is x squared minus 1. We want to set the derivative equal to 0 to find the critical numbers. At this point, you can either factor that x squared minus 1 is x plus 1 times x minus 1 and set each factor equal to 0, or you could just add the 1 to both sides and then take the square root of both sides, and the square root of 1 is plus or minus 1. Those are your critical numbers that go on the increasing decreasing chart. Once you get those, you want to do a test value in each of the intervals formed by the critical numbers. So you want a number to the left of minus 1. I would probably choose minus 2. You want a number between minus 1 and 1. I'd probably choose 0. And you want a number bigger than 1. I would probably choose 2. What do you do with those numbers? You plug them into the derivative, because the derivative tells you what the slope is, and the slope tells you about increasing decreasing, which is what we want for our increasing decreasing chart. So you take minus 2 and you plug it into the derivative. Square minus 2, you get 4. 4 minus 1 is 3. That's a positive value. That means the function's increasing to the left of minus 1. Then you do the same thing with the test value of 0. Plugging it into the derivative. 0 squared is 0, minus 1 is minus 1. That means the derivative is negative, which means the slope is negative, which means the function is decreasing on that interval. Then you take the test value and plug it into the derivative for the one to the right of 1, which we chose 2. 2 squared is 4, 4 minus 1 is 3. That's positive, which means the function is increasing on the interval once you get past 1. Increasing to the left of minus 1 until it gets to 1, decreasing between minus 1 and 1, increasing after 1. Increasing decreasing chart is critical to this. Now you've got to figure out what type of extrema you have. As I said, it can be maxes or mins, and it's possible for a critical number to represent neither. How do you tell? Well, let's just start off with the maximum. The behavior around a critical number that's a maximum is the function is increasing to the left and decreasing to the right, as is pictured here. And remember, when I say f prime of x is greater than 0, if something is greater than 0, it's positive. So I'm saying that the derivative is positive, which means the slope is positive. So the curve is headed up until it gets to the critical value, and then it starts down, because f prime of x less than 0 means negative. So if you look back up at our increasing decreasing chart, you can see that behavior around minus 1. It's increasing to the left of minus 1 and decreasing to the right. We've found the critical number for a relative maximum. The relative maximum itself is the function value. So what you have to do, and if you're looking for the whole xy point, it's made up of the critical number as the x-coordinate with the critical number plugged back into the original function as the y-coordinate. Remember, whenever you're calculating the value that represents the y value of a function, you have to go back to the original function. The original function is your y. F of x is the same as y. So if you want to know what y is, of course, you have to go back to the only equation that has y. So we want to plug minus 1 into the original function and figure out what y is. So let's go off to the side and do that. If I take minus 1 and plug it back into the original function, I don't want to spend a great deal of time on arithmetic. If you cube minus 1, that's minus 1 times minus 1 times minus 1. It comes out to be negative 1. Negative 1 times a third is negative a third. And then on the end, you've got minus a minus a 1, which is plus 1. So you really end up with 1 minus 1/3, which is 2/3. That's the y value that we were looking for. Plug it back in, and you can see that the relative maximum occurs at the point minus 1 2/3. Technically, the minus 1 is the x-coordinate of the relative maximum. 2/3 is the relative maximum, and the point where that occurs is the point minus 1 comma 2/3. So it depends on what the problem is asking for as to how you answer the question. Sometimes they'll just say, where does the relative extrema occur? And the answer will be minus 1. If they say, what is the relative, in this case, maximum, it would be 2/3. And if they said at what point does it occur, you would write the entire point minus 1 comma 2/3. So you just have to look at what they're asking for. So that's the relative maximum. Now look, for a relative minimum, the behavior switched. If the derivative is negative, less than 0 means negative to the left, but positive to the right, that is the hallmark of a relative minimum. And if you look back at your increasing decreasing chart, you can see that behavior around x equal to 1. So the relative minimum is at 1 comma whatever you get when you plug 1 back into the function. Again, remember, we're going back to the original function. Whenever you want to find the y value, go back to the original function because that's where the y is. So if I go back up here, let's move up, plug 1 into the function. Again, don't want to belabor the arithmetic. I'll end up with negative 2/3. So that is the y value of the point that corresponds to 1 as the critical number. So the critical number at 1 represents a relative minimum. The relative minimum is actually negative 2/3, and the point where the relative minimum occurs is the point 1 comma negative 2/3. So just be careful about what the problem is actually asking you to do. The process is fairly simple, and it centers around that increasing decreasing chart and how you interpret it. Very straightforward. You just have to know your basics, and you especially have to know how to do that increasing decreasing chart. I thought it would be a good time to summarize a little bit. I'm just going to throw out what we just said and put it where you can look at it without having a problem embedded in the middle of it. For a relative extrema, if you've got a critical number C, if the behavior is down, up, that critical number is the x value of a relative minimum. If the behavior is up on the left and down on the right, up on the left, down on the right, then that critical number is the x coordinate of a relative maximum. Just want to say these things a lot so you get used to hearing them. If f of c is a relative extremum, either a maximum or a minimum, we say that that extrema occurs at x equals c. So we're just learning some vocabulary and you're getting used to hearing the word said. Conversely, you could also say if f has a relative maximum or minimum at x equals c, then x equals c is a critical number of the function f. Beyond the vocabulary, we can put all of this together in a procedure that we'll call the first derivative test. Once we determine that c is a critical number of a function f, this first derivative test that tells us about relative extrema enables us to do the classification just like we talked about. So all I'm doing now really is documenting what we've already done and putting it in a more formal format. So don't let the word scare you. It's just a documentation of what we just did. So here is the formal version of the first derivative test for relative extrema. The function has to be continuous on some open interval around some critical number c, and it has to be differentiable on the open interval as well, except possibly at the critical number itself. Once you've got all those conditions satisfied, here's how you classify the value of the function at that critical number. If the derivative is negative to the left and positive to the right, then the function value at c is a relative minimum. It's just what we said earlier. Down to the left, up to the right. A negative derivative value to the left, a positive derivative value to the right. You found the x coordinate of a relative minimum. If it's reversed, if the derivative is positive on the left and negative on the right, that's up, down, then you've located the x coordinate of a relative maximum. And if it doesn't change, if it's either down, down, or up, up on both sides of a critical number, then that critical number is neither a maximum nor a minimum. So you don't have to have a maximum or a minimum at a critical number. You have to have a change of sign of the derivative around that value c in order to have a critical number that's actually a max or a min. And you can look at it and see what, just really simple visualizations of what this means. For instance, if you have a simple looking, I guess a parabola is one of the simplest ways to look at it. If the parabola opens up, you get a decreasing function to the left. In other words, the derivative is negative, and you get an increasing to the right. So if you want to visualize something like that, a parabola opening up might be the best way to visualize it. If you flip the parabola upside down, you have a derivative that's positive on the left and negative on the right. That turns out to be a x-coordinate, an x value that represents a relative maximum. And it's possible you get neither. If you've got a point C labeled like this third possibility, you get a positive derivative on the left and a positive derivative on the right. In other words, it's increasing right through that point. That's not a max or a min, and it can be reversed so that it's negative on the left and negative on the right. So every critical number does not have to be a max or min. You have to get that change in sign of the derivative around it. So look at this as a summary or a distillation of what we were doing, not something that we're learning right now that's brand new. This is what we've been talking about for the last 15 minutes or so. What I'll call the guidelines I'm going to list now. The first thing you want to do when you see a problem that you want to do a max min for is take the derivative. Find f prime of x. Then you want to find the critical numbers and use them to find the test intervals. In other words, you're trying to build the increasing decreasing chart. Once you get the increasing decreasing chart, you want to do test values within each interval and plug them into the derivative. If the value of the test number that you chose comes out positive, that means it's increasing on the interval. If it comes out negative, it means it's decreasing on that interval. And finally, for each critical number, use that first derivative test to classify a critical number as either a max or min or neither. If you get the up-down behavior, you found a max. If you get the down-up behavior, you've got a min. And if you get up-up or down-down, it's neither. So I'm trying to say this in a bunch of different ways, and I'm trying to summarize what we've done, but the idea is very, very simple. Take a derivative, find the critical numbers, build your increasing, decreasing chart, use your test values, and then use the first derivative test to classify what you found as either maxes or mins or neither. Fairly simple. Just formalizations of what we've already talked about. Another example. Find all relative extrema of the function f of x equals x to the fourth minus x cubed. This is a simple polynomial function, so there are not going to be any surprises. What do? Here are your guidelines. Find the derivative. Simple enough. Find the critical numbers. How do you do that? Well, you're going to set the derivative equal to 0, but if there's something to be factored in that expression, you probably want to do that first. At some point, you're going to have to do it if it needs to be done, but we'll go ahead and do it first. There's an x squared inside of both those terms, so I factor out an x squared. That leaves me with 4x minus 3. And once you get it factored, you're going to set the thing equal to 0. When you've got a product equal to 0, that's the same as setting each factor equal to 0. So you want to set the x squared equal to 0, and you want to set the 4x minus 3 equal to 0. When you set x squared equal to 0, that means x is 0. And if you set 4x minus 3 equal to 0, you'll push the 3 to the other side and divide by 4, and you'll get x equals 3/4. So put your pen to paper on that if you want to make sure you're with me. But your critical numbers come from taking the derivative, setting it equal to 0, and if you need to, you can factor and set each factor equal to 0. Those are your critical numbers. In this case, 0 and 3/4. Put them on the number line. Remember, you're building your increasing, decreasing chart. Take a test value in each interval. To the left of 0, I'll use my test value of -1. Between 0 and 3/4, I'll choose a half. And bigger than 3/4, I'll choose 1. What do you do with those test values? You plug them into the derivative. Now, I'm not going to do much with the arithmetic here. I'm sure you can follow along. So if you take -1 and plug it into that derivative, you're going to get -7. You really don't care that it's -7 so much as the fact that it's negative. That means the function is decreasing to the left of 0. Then you take your second test value, in this case 1/2, plug it into that function. Again, I'm not going to belabor the arithmetic, but if you do that, you're going to get 1/2 squared times -1. 1/2 squared is 1/4, and a fourth times minus 1 is minus 1/4. Again, you don't so much care that it's minus 1/4 as the fact that it's a negative. So you get a negative on both sides of 0. That's a down, down. That's not going to be a relative extremum. Now you take the last test value, 1, plug it into the derivative, calculate, and you get a positive 1, which again, I'm only interested in the fact that it's positive. So the behavior is going to be down, down, up. And if I go back and look at my first derivative test, down, down is neither, but around 3/4 I've got down, up, and down, up. That down, up behavior is that of a relative minimum. So I have a relative minimum at 3/4. There is no relative extreme at 0 because I get a down, down. I don't get a down, up. I don't get an up, down. I get a down, down. No extrema there. The relative minimum is at 3/4. To find out what it is, I plug 3/4 into the function, the original function. Remember, the max or min is a y value, and to get a y value, you've got to go back to the original function. So I'm going back to the original function and plugging in. And remember, the original function was f of x equal x to the 4th minus x to the 3rd. So if you take 3/4 and raise it to the 4th power, again, I don't want to belabor the arithmetic, you get 3 to the 4th over 4 to the 4th. 3 to the 4th is 81, 4 to the 4th is 256, minus 3/4 cubed, that's 3 cubed, which is 3 times 3 times 3 is 27. 4 cubed is 4 times 4 times 4, which is 64. You cannot add or subtract fractions without getting a common denominator, so you have to change that 64 denominator to a 256 by multiplying top and bottom by 4. Now I'm going to do that, and that gives me 81,256 minus 108,256, and then once you get the common denominator, you can subtract the numerators and you get negative 27,256. So as awkward as that was to calculate, there's nothing difficult about it. That is the relative minimum. So the problems can have nasty arithmetic occasionally, but the process is fairly simple and straightforward. If you wanted a graph to verify it, you don't need the graph to do any of this work, but that's what it looks like. And you see that there really is a relative minimum at the point we said it was. But you don't need the graph to know that. Now let's turn our attention to something related but more broad, the idea of absolute extrema. When I say the word relative, it means local, in the area. So if I have a hill in my neighborhood, the top of that hill might locally be the highest point in the neighborhood, but it's not the highest point on Earth. It's a local or a relative maximum. When I say absolute extrema, that's going to be absolute maximum or an absolute minimum. That means anywhere, not just around close to you. And we'll have the term absolute maximum as opposed to relative maximum, and we'll have the term absolute minimum as opposed to relative minimum. Maybe this will help. I pulled this off the internet, and it talks about the highest and lowest points on Earth. If you look, it tells you that Mount Everest is the highest point on Earth. That would be the absolute maximum for the entire Earth. Though if you think of the height of that mountain as being a y value, that y value would be the absolute maximum on Earth. On the other hand, it tells you that Mount Fuji is the highest point in Japan. That would be considered a relative maximum. As long as you're near Mount Fuji in Japan and you look around, that is the maximum value in that area. That's a relative maximum. So the height of Mount Fuji is a relative maximum, whereas the height of Mount Everest is the absolute maximum. Now it turns out if you're an absolute maximum, you can also be a relative maximum. So if you're standing around Mount Everest, it's also, not only is it the tallest thing on Earth, it's also the tallest thing in your neighborhood. So it's a relative maximum and an absolute maximum. And in case you're interested, here's the definition of absolute extrema. I'm not so worried about you know the definition. All it's saying is that you have an absolute minimum on an interval if when you plug that value into the function, you can't find anything else that will give you a value that low on the entire domain of the function. And it's an absolute maximum interval when the opposite is true. You can't find any value you can plug in on the entire domain that gives you a value any higher. No need to memorize the definition, but that's the formal definition of absolute extrema. It is really important that you understand the distinction between relative extrema and absolute extrema. So I'm going to show you one more thing to try to help you get this into your head, into your vocabulary, so to say, so that when you think about it, you're not confused about what you're being asked to do. The basic idea is that we're always, when we're talking about absolute extrema, we'll be given a closed interval where we're looking over that entire interval. So in this case, the picture shows an interval from A to B, and you just got a graph there. Now notice several things about this graph. Just like you can say that Mount Everest is both an absolute max and a relative max, it can be true for a minimum as well. The absolute maximum in the entire graph is the far right endpoint. There is no place any higher. However, the relative maximum, which is to the left of the absolute maximum, if you think of this as being some point C, and you're looking in the neighborhood of C, there is no value any higher than that value in the neighborhood. So that's a relative maximum, but it is not the absolute maximum because this point has a larger y value than this point. In this example, you have a relative maximum that is not an absolute maximum, and you have an absolute maximum that's not a relative maximum. But look at the minimum. The relative minimum is also the absolute minimum. If you look around this point, they call it C, in that neighborhood, there is no point any lower than there. So that is the definition of a relative minimum. But it is also the absolute lowest point on the curve. There is no y value any lower on that curve than the y value at that point. So that point is both a relative minimum and an absolute minimum. So I hope this graph helps you sort of make some distinctions that are important when you're talking about absolute versus relative. It also leads to something, if you just look at this, called the extreme value theorem. If your function is continuous, in other words, there are no gaps, holes, anything to stop it from being drawn by a pen or a pencil without lifting it from the paper. Anytime you have a function like that on a closed interval, it will have a minimum value, absolutely, and a maximum value, absolutely, on that closed interval. No way that it can't, because of the fact that it's a continuous function. And the extrema can occur at the endpoint. It can be at the endpoint of the interval. So it's really just like doing the relative extrema, except you have to consider the endpoints as well. The endpoints don't show up as critical numbers. You have to just put them in manually. So when you're doing these problems, and you're doing an absolute extrema problem on a closed interval, you've got to do the increasing, decreasing chart just like you did for the other, but you've also got to check the endpoints, because the endpoints can be higher or lower than anything you find from the critical numbers. So it's what you were doing before with the increasing, decreasing chart, finding the relative maxes and mins, but you've also got to check the endpoints and throw in their y values as well and see if any of those exceed the others. Hope that makes sense. So just some overall guidelines. You want to, when you're doing these problems, when you have a continuous function over a closed interval, what you want to do is find the critical numbers, just like you were doing with the increasing, decreasing chart, and then find the y values for each of those critical numbers. But also find the y values for the endpoints. Now, if you like, you can actually do the increasing, decreasing chart and then throw in the endpoints, but as long as you have a continuous function, you don't really even have to produce the increasing, decreasing chart. So really, if you find the critical numbers, evaluate the y values for the critical numbers, then evaluate the y values for the endpoint values. Whatever y value comes out the very least is the absolute minimum, and what comes out the biggest of all is the maximum. So don't make this harder than it really is. When you've got absolute Extrema and you've got a continuous function over a closed interval, just find the critical values, plug them in and find the y values. Take the endpoint x's, plug them into the function and find their y values. The biggest y value you find is the absolute maximum from among all those numbers, and the smallest is the absolute minimum from all those numbers. Let's turn to a concrete example. Suppose we want to find the absolute minimum and maximum values of this function f of x equals x squared minus 6x plus 2 on the closed interval from 0 to 5. Here are the guidelines that we developed for going through, and you're going to find that in some sense, even though it sounds like you have to do a little more work for the absolute extrema because you have to throw in the endpoints as well, it turns out that it's actually going to be more straightforward, and you'll see as we go along why that is. The first thing you want to do is find the critical numbers that are in that open interval, in this case from 0 to 5. You know that finding critical numbers for a polynomial function involves taking the derivative and setting it equal to 0. Well, this is an easy derivative, 2x minus 6. Set it equal to 0. Move the 6 to the other side, divide by 2, and you find out that x equals 3. Now here I might also add that one of the nice things about dealing only with continuous functions over closed intervals, which is what we're going to be doing for our absolute extrema, is you don't actually have to do an increasing decreasing chart. You only have to find the critical numbers that are within that interval, because knowing that you're locked in that closed interval and that the function is continuous makes the increasing decreasing chart really unnecessary. All we need to do is find those critical numbers that are in that interval, in this case from 0 to 5, and then find their y values. Well, we've already found the only critical number, and that's x equals 3, and it is in the interval from 0 to 5. Had the answer come out to be like 7, which is not in an interval, you just toss it and there wouldn't be any critical numbers. So you're only looking for critical numbers, and you're only looking for critical numbers that are in the interval. Step 2, evaluate the function at each of its critical numbers in that interval. Now again, evaluating means finding the y values. And when you go to y values, you always go back to the original function. The derivative tells you about the slope. If you want the y values, you have to go back to the original function. So we're going to plug 3 back into the original function, do the arithmetic, simplify, and you find out that f of 3 is equal to minus 7. Okay, so we found the only critical number in the interval, and we found the y value of that critical number. Now we take the endpoints into consideration. So we take the a and the b, in this case the 0 and the 5. You plug 0 into the original function to find its y value, and you plug 5 into the original function to find its y value. So if you plug 0 back into the original function, do the arithmetic, you find out that f of 0 is 2. Do the same thing for the other endpoint 5, plug it into the original function, do the arithmetic, and you find out that f of 5 is equal to minus 3. Now here's where you get to the point where you realize that this process is actually a little more straightforward than finding the relative extrema, because you don't really have to do the increasing decreasing chart. All you have to do is take the numbers that you found, the critical value with its y value, and the endpoints, plural, and their y values, and put them in order of the y values from smallest to largest. Actually, you could do largest to smallest, but let's just be consistent and say smallest to largest. So we take the y values and put the list in order. The smallest of the y values is the minus 7, so it goes first. The next smallest y value is minus 3, so it goes second. The largest of the y values is 2, so it goes third. So from smallest to largest, the y values are minus 7, minus 3, and 2. And all you have to do is look. The smallest of the y values is the absolute minimum. The largest of the y values is the absolute maximum. So in some sense, this is actually easier than finding the relative extrema, because with all the restrictions we have on the problems we do absolute extrema for, we don't really have to do the increasing decreasing chart. Makes the problem a little bit more straightforward. You could look at a graph to verify that this is correct, but you don't need the graph to get the answer. Let's look at another example. This is not a polynomial function, but it turns out that as long as you have continuity in the closed interval, it really doesn't matter that it's polynomial. Taking the derivative might be a little harder, but that's okay. So this is a rational function. H of t is t over t minus 6, and we're only interested in the interval from 7 to 13. Now we have our guidelines from before, same as before. Let's just step through. The first thing we're going to do is find the critical numbers, and the critical numbers involve taking the derivative and set it equal to 0. This is where the problem becomes a little bit more difficult. It's probably not the right word, a little more time consuming, because to find the derivative of a rational function, we have to use the quotient rule. Quotient rule takes a little more time than just taking the derivative of a polynomial function. So if you think of the t as the numerator being high and t minus 6, the denominator being the low, the quotient rule says low d high minus high d low over low squared. Low is the denominator, so that's t minus 6, times the derivative of the numerator, derivative of t is 1, minus high, which is the numerator, that's t, times the derivative of the denominator is 1, all over the denominator, which is t minus 6, all squared. Simplify that, easy simplification. You get t minus 6 minus t up top. T minus t is going to be 0, so you end up with the derivative of h is minus 6 all over t minus 6 quantity squared. Now what we have to do is set that equal to 0, and you're done for a polynomial function. But for a rational function, it's a little bit different, because when you're finding the critical numbers for a rational function, you also have to worry about places where the denominator could be undefined. If it's just a polynomial function, all you have to do is worry about where the derivative is equal to 0. That's all you have to worry about. But when it's rational, you also have to look at what makes the denominator undefined. But either way, this is pretty easy, because when you look at the fraction being 0, there's only one way you can make a fraction 0, and that's to make the numerator 0, because the denominator can't be 0. But the numerator is just the number minus 6. How do you make minus 6 0? And the answer is you can't. So there isn't any value that makes the derivative 0, because the derivative is a fraction, and you only have to look at the numerator when you're deciding if you can make a fraction 0, and the numerator is just the number minus 6, which is most assuredly not 0. So there is no critical number from having the fraction equal to 0. But the other condition about the derivative being undefined happens when you get in a situation where you're dividing by 0. Well, it's pretty easy to see. In the denominator, if you plug a 6 in for t, you divide by 0. So that is a value where the derivative is undefined. So the other critical value condition tells you that the derivative is undefined at 6. So you say, okay, that's going to be a critical number, and I have to consider it. On first blush, that's true. But notice that 6 is not inside of this interval from 7 to 13. The critical numbers have to be in the interval. That's not the case. 6 is not between 7 and 13, so 6 gets tossed out. So the bottom line is there are no critical numbers, because the only thing that looked like it would be in the beginning got tossed out because it was not in the interval. So there aren't any critical numbers. So all that's left to check are the endpoints. What do? Again, to get y values, you go back to the original function, and you're only left with the endpoints. You take the left endpoint 7, plug it back into the original function, and you get 7 over 7 minus 6, which is 7 over 1, which is 7. And then you plug in 13, you get 13 over 13 minus 6, that's 13 sevenths. And there are only 2, so putting them in order is sort of redundancy. You look for the biggest and the smallest y values. Well, the biggest y value is 7. 7 is bigger than 13 sevenths. So that means that the absolute max is 7. And of course, there's only one more, so it must be the min. The absolute min is 13 sevenths. So at first, you see this problem that looks more difficult than the polynomials we worked earlier. But other than taking the derivative by the quotient rule and having to look at the denominator as well as the numerator, it's really not bad at all. But do pay attention. This problem highlighted the fact that you have to throw out any critical number that is not in that interval. The absolute extrema problems are actually, in some sense, easier to do than the relative extrema problem. Let's wind this up by looking at some more of this stuff graphically. This is a problem that you might see on your homework, something similar to this. And I just want to go through and show you how you can think this through. This problem gives you some conditions on a graph, and they want you to pick the graph out of the list of possible graphs that satisfy these conditions. So the conditions are, there's a relative minimum at x equal minus 1. There's a critical number at x equals 0, but no extrema. In other words, no max or min. There's an absolute max at x equal 2. There's an absolute minimum at x equal 5. And here are the 4 graphs that you have to choose from. Now, I call this a detective problem. You're just looking at all the clues and you're eliminating suspects until you're finally left with the only possible one that could be the answer. That's the way I look at this. So let's just take the conditions one at a time and look at their implications. That first condition, having a relative minimum at x equal minus 1, means the behavior at x equal minus 1 looks like a parabola that opens up. In other words, it decreases on the left and it increases on the right. That's the behavior around x equal minus 1. So that first condition implies that when you get close to minus 1, you get that sort of valley shape. The second condition says there's a critical number at x equals 0, but there's no max or min. What does that look like? Well, that means you get this down behavior or up behavior around the point. So you have a point, but there is no change from up to down or down to up. There's either a down down or an up up. That's the behavior at x equals 0. Third condition says there's an absolute maximum at x equal 2. Well, what does that mean? That means you get the behavior that says that the highest point on the entire graph, bar none, is at x equal 2. So when you look at the graph, there's no point on it that has a y value bigger than the y value at x equal 2. And the last condition says the absolute minimum is at x equal 5, and that's the flip side. There's no lower point on the graph than the point at x equal 5. You've got to take all those 4 conditions and apply them and see what happens. So let's do that. Let's just start off looking at that first condition, the behavior at x equal minus 1. Well, you can see that the behavior at x equal minus 1 for that first graph is up followed by down. We're looking for down followed by up. So it can't possibly be the first one. And the same thing's true for the second one. The second graph is up followed by down. That can't be right. So we've already eliminated choices 1 and 2. That can't possibly be. We've already got a 50-50 shot at it now. We'll keep moving along. If you look at the x equals 0, it's supposed to be either down, down, or up, up. But if you look at the third graph, around 0, remember we're looking at around 0, it goes up followed by down. That's wrong. It's not supposed to do that at 0, so that knocks out the third possibility. Technically, if we haven't made a logic error or error in thinking this through, we've already decided now the answer has to be the fourth one, but you can go through it one at a time and see that all those conditions are true. At x equal minus 1, you get the right kind of behavior. You get the down followed by up. That's what we're looking for, down followed by up. The second condition, you're either looking for down, down, or up, up. And in this case, around there, we're getting up, up. That's okay. The next condition says at x equal 2, you get the highest point on the graph. And if you look at x equal 2, that assuredly is the highest point on the graph, so that's good. And the fourth condition says when you go to 5, you get the lowest point on the graph, and again, that's assuredly true. So this is one of those detective problems where you take the clues, the conditions or the clues, and you work your way through and eliminate all the suspects until you're left with just the one that can possibly be right. It's actually sort of fun. So the fourth graph is definitely the correct answer. Let's end with a business example of finding a maximum profit. Suppose we have a company that's making some product, we'll call them burgers, and we have a profit function, which is polynomial in this case, that describes the profit from selling X burgers. And we want to find the sales level that will give maximum profit. Now, if you're in business, you're very interested in making a maximum profit, so this should be an interesting problem. I will say if you've got an expression that has a term that's x to a power divided by a number, on the face of it, it looks like you'd have to use the quotient rule to solve that. But dividing by 20,000 is the same as multiplying by 1/20,000th. If I'm going to be taking a derivative of a term that looks like that, the first thing I'm going to do is, instead of dividing by 20,000, I'm going to multiply by its reciprocal, 1/20,000. The only reason I'm doing that is I want to avoid using the quotient rule. So my first suggestion is, if you see a problem like that, where you have a power of x in the numerator and just a number in the denominator, is to write it like this. And that allows you just to use the power rule. Because if we're trying to find the maximum, we're going to be taking a derivative. Well, now this is easy. The derivative of 2.44x is just 2.44. And the derivative of a number times x squared is just the number times the power by the power rule. That's 2 times 1/20,000th, which is 2/20,000. And then you subtract 1 from the exponent, and instead of it being x squared, it becomes x to the first, which is just x. And that gives you the second term's derivative. And of course, the derivative of number is just 0. So you end up with a very simple expression. And remember, we want to find the critical number, so we want to set that equal to 0. So we take the expression we have and we set it equal to 0. Now, it's just simple algebra from here on. What I would probably do is move the negative term over the other side and make it positive. At this point, if you want to get rid of the fractions, it's pretty easy if you just multiply both sides by 10,000. If you multiply both sides by 10,000, the 10,000s on the right divide out, and you're just left with x is equal to 2.44 times 10,000, which is 24,400. That's the critical number. And in reality, you've answered the question. The sales yielding maximum profit is 24,400. So if you sell 24,400 burgers, given this profit function, it will maximize your profit. Now, instead of ending here, I want to say two more things. The first thing is, technically, we should do an increasing decreasing chart to make sure it turns out to be a maximum and not a minimum. But what I want to say about that is, on these application problems, they'll never try to fool you. If you just get one critical number and they want a maximum, you can assume it will be a maximum. And if you want a minimum, it'll be a minimum. They're not going to try to fool you. So technically, you should do the increasing decreasing chart to show that it really is the max or the min that you're looking for. But in reality, not really necessary. The last thing I'll say is, sometimes they want to know what the actual profit will be. Now, I know that I can sell this many burgers, but how much is the actual profit? And to answer that, you would plug the x value back into the original function. Remember, you always go back to the original function to find y values, or in this case, profit values. P is the profit. I won't go through the arithmetic, but you might want to try it on your calculator to make sure you can actually do it, because you might be asked to do it. But if you do it correctly, you'll get a profit of $24,768.